Hey folks, I got a circular dynamics example for you involving a fighter jet or something in the midst of inverted flight. So let me explain the picture to you, and then you can pause the video and copy all the stuff down. So it's a pilot. Now it's not to scale, obviously, but it's a pilot going in a vertical circle in the sky. And at this point, the pilot is starting to go upside down. Okay, so here is when the fighter jet, at this moment right there, the fighter jet was going straight up, and she's gone past that point, and now she's starting to go upside down. And we're going to determine two things: the force that the seat exerts on her, and in order to do that, we're also going to need to figure out the radial acceleration. So if you need a moment to pause the video and copy all of the information down, now would be a great time. All right. So this is it's a straightforward problem, except for the wording is a little tricky. It says force at the seat, the force of the seat, or the way a problem would be worded would be what force does the seat exert on the pilot? Okay. So I'm going to show you at least one way to do that. There's probably more than one way to do this, but here's the most straightforward way. So first of all, you'll note that she is speeding up at this moment. She has a tangential acceleration. So she's, hitting the gas on the airplane, hitting the throttle, and speeding up as she does this. So I'm actually going to determine the radial acceleration first, because that's really simple. So the magnitude of the radial acceleration is simply v squared over r, which is 150 squared divided by 200, which if you plug it in your calculator, you get 112.5 meters per second per second. Now, a note, in a real life problem, odds are the pilot would be passed out at this point. That's like about almost, it's over 11 Gs, like almost 12 Gs. So this is probably not a real problem, okay? But it's fun anyway. So there you go. Now, the force of the seat part, this is the part that's a little hard, okay? So we're going to start with the FBD of the pilot, okay? So here's the pilot. Okay, so what forces act on her? Well, she's on Earth, so force of gravity is going to act down. I'll just label that mg right away. And then the seat is going to push on her. Now, that's a little tough to kind of, figure out exactly which direction that goes at the moment. You probably, if you look at the picture and you think about that she's speeding up on the way up, there's definitely going to be somewhat of an upward force. But since she's also going in a circle, there's going to be an inward force. So, the force of the seat would probably do something like that, maybe, okay? Again, I'm just kind of estimate, okay? So there we go. There's the force of the seat, okay? Now, just like in all the other problems we've done, we're going to take those forces and break them down to components that are either, okay, parallel to the motion or perpendicular to the motion, okay? So first of all, mg, okay, that's neither parallel nor perpendicular to the motion, so we got to break that down. So there's going to be a component that way, okay, and that's going to be mg. And now here's the question: is it sine or cosine? Okay. Well, if you imagine at this intersection here, if I drop a line straight down, this angle here and this angle here will be congruent. If you really want to proof that, it's a good geometry question. Ask me later. But those two angles are congruent. So we're looking at the adjacent leg of that triangle. So that's cosine of the angle. Okay. And then there'll be a component toward the center of the circle. That's mg sine of the angle. Okay. Now, force of the seat, okay? We don't know this angle, all right? So I'm going to kind of cheat on this a little bit. We do know, looking at the picture, that there's probably two components. It's probably not just parallel, nor is it just perpendicular to the motion of the pilot at this moment. So, in other words, like I'm going to break this down into two components. So here is the component of the seat force. I'm going to call it force seat parallel to her motion. And there's going to be a component inward, and that's force seat perpendicular. Now, again, I don't have an angle there, so I can't do a sine or cosine or anything, but I do know there's two components to the seat force. So here's what we're going to do. We're going to find each component of that seat force, and then we just Pythagorn them to get the total seat force, and then you'd also know the angle from the triangle, okay? All right, now here you get a choice on which direction to analyze first. It wouldn't matter which one. I'll do the perpendicular first. No, I'll do the parallel first. Actually, I lied. So let's look at net force in the parallel direction has to equal m times a in the parallel direction. Okay. Now the parallel direction is she's speeding up in this direction. So I'm going to call that positive for the parallel direction. Okay. So in which case you would get force seat parallel minus mg cosine theta equals ma parallel, which is a sub t, or tangential acceleration. Okay. And then now, by the way, at this point, if you've understood what we've done thus far and you've gotten this far in the problem, the rest of the problem is pretty easy. The hardest part, and the part you should be spending the most effort and time on, is this part here. If you can identify the forces and which way they go, you're 90% done. The rest of it's just a little bit of math, okay? So in every problem, you're going to notice that I draw a sketch of it, and then the College Board FBD, and then the broken down into components FBD, okay? All right, so going back to our math here. All right, so I got F seat parallel, which one of the things I'm trying to figure out, minus mg cosine theta, so we'll plug those in. mg is 9.8, cosine 30 equals m, which is 100 times 5, and you end up with a force of the seat in the parallel direction to our motion is, if I plug in my calculator right, I got 1,349 newtons, okay? Which is a little more than her weight. Her weight would be about 980 newtons, so this is about 1.5 times that, give or take. All right, now in the perpendicular direction, okay, so we're going to do net force in the perpendicular to our motion direction equals ma perpendicular, okay? I always make inward toward the center of the circle positive. That's going to be this way in the picture, okay? So that's going to be this way in our FBD. So both those forces act inwards. So we got force seat perpendicular plus mg sine theta equals ma perpendicular. Okay. Oh, and a perpendicular, what is that? That's our radial acceleration, which we already calculated, right? That's our 112.5. Okay. So we've got it. FC perpendicular plus m, which is 100, g is 9.8, sine of our 30 degrees, sine of 30, equals m, which is 100 times 112.5. And if you solve for FC perpendicular, you get a darn big number. You get 10,760 newtons, which is about 11 times her weight. So there's a lot of force acting on this pilot, and she's probably in trouble, passed out at very least, okay? And then at this point, if you want to find the total force of the seat, you would just Pythag these, right? You would Pythag the force seat parallel, square that, plus force seat perpendicular, you got to square that. I plug the numbers in my calculator. I got 10,844 newtons. Okay, so that's the total amount of force the seat exerts on her. You could also find an angle. The parallel component, that's your 1349. That's the parallel component. Your perpendicular component is 10,760. This angle here is 30 degrees. You could find this angle here, okay, by, inverse tangent of 10,760 over 1349. So then if you found this angle, that's this one here, that would be an angle inward from the tangent of the circle. If you wanted with the vertical, you would then add 30 degrees to it and say, it's, counterclockwise blank degrees from the vertical. So it would kind of depend if they even ask you that or not, okay? So again, splitting your forces up into parallel and perpendicular components to the motion, analyzing each of those two directions. The key here is being able to draw the FBD. I cannot emphasize that enough. It's incredibly important. So I hope that was helpful, and I've got a few more examples to come. Have a good one.